We'll start today's section 10.2 notes, and we'll still continue to do probability questions. The first question, in the children's game, Build a Farm, each player first spins a spinner. Half of the time, the spinner comes up red, and half of the time, the spinner comes blue. If the spinner is red, the player reaches into the red box. If the spinner is blue, the player reaches into the blue box. The red box has 10 chicken counters, 10 pigs, and 10 cows, while the blue box has 5 chicken and 4 pigs and 1 cow. So we want to do a tree diagram to represent this scenario. Looking at the tree diagram, you will have to look at the first spinner first. And with the first spinner, so here's my first spinner. With the first spinner, I have 2 different possibilities. Here's my red, and here is my blue. So I will put here, this is your first spinner. So here's your first spin. First spin. If you had the first spinner and you spun like you had either red or blue, from the red you have different possibilities, which is you can get a chicken, you can get a pig, and you can get a cow. But not all of them are equal likely to happen. With the red and blue, the first spinner, each one of them has a probability of half. So I'll put, you need to make sure that you put down the probability on each one of the branches. Without the probability on each of the branches, imagine it would be a two-way table without the numbers inside. So make sure that, or outside, like, your boxes. So make sure that you're putting down the probability on each one of those branches. If you get into red, if you had red, then the player reaches into a red box, and if the spinner is blue, the player reaches into the blue box. If you have, the red has 10 chicken, 10 pigs, and 10 cows. So each one of them will have a probability of 1/3. So 10 out of 30, or 10 out of 30, or 10 out of 30. So simplifying this one, each one of them will have 1/3 probability. If you reached into the blue box, then the blue box, you will get 5 chicken, 4 pigs, and 1 cow. So I'll start by doing my probability for my tree diagram, and I'll calculate each one of the probabilities. So I have chicken, I have also pig, and I have cow. The probabilities are not the same. So the probability of getting a chicken is 5 out of the 10, which simplifies to 1/2. The probability of getting a pig is 4 out of the 10, which simplifies to 2/5. And the probability of a cow, it's 1 out of the 10. Now I'll start by calculating the probability for each one of those branches. So the probability of getting a red and a chicken would be 1/2 times 1/3, which is 1/6, which simplifies to 0.16. The probability of a red and a pig would be 1/2 times 1/3, which is 1/6 again, which simplifies to 0.16. Finally, the last one here, 1/2 times 1/3, which gives us the probability of a red and a cow, and that's again 1/6, which is 0.16. The second part, 1/2 times 1/2 will give you the probability of a blue and chicken. So 1/2 times 1/2 is 1/4, which is 0.25. The probability of the following branch is 1/2 times 2/5, which is equal to 2/10, which simplifies to 0.2. The last branch is 1/2 times 1/10, which is 1/20, which simplifies to 0.05. Second question, what is the probability of getting a cow in one turn? They didn't specify whether it was a blue or a red, so it would be this branch. So it would be this branch and this branch too as well. So everything that was cow, so it would be the probability of getting a cow is equal to the 0.16 from the first branch, repeating, plus the second branch is 0.05. Adding them up together, it would be 0.2167. So the probability of getting a cow would be those two branches added together, which is 0.2167. The following question, you will see it's the same, you're talking about the same question. However, they took the information and they made a two-way table. So here's a two-way table that represents the same scenario. So you have chickens from the first spinner, which is the one that was red. It was chicken, pig, and cow, and you had 1/3 for each one of them. For the second, you will see also a chicken and pig and cow from the second spinner, which is the blue, and it was 1/2, 2/5, and 1/10. So this is just a different way that you can put the information, but in a two-way table. There's two different ways that you can set up your information for a problem. It could be a two-way table, it could be a tree diagram, and you can most of the time you can choose one of them. But if you have more than two variables, then you cannot do a two-way table. You're going to be stuck using the tree diagram. D, what is the conditional probability? What is the conditional probability that a child had spun red, knowing that the child get a cow? So you want to find the probability that you get a spun red, given that you get a cow. This probability, when we talked about the given, it was easier to think about it from the two-way table. So the probability of A given B is equal to the probability of A and B divided by the probability of B. If I go take the same rule that you have here and apply it to the question that we just trying to figure it out for D, it will be the probability of red and cow divided by the probability of cow. The probability of getting a cow, we just finished that in part B actually, and it was 0.2167. The probability of a red and a cow, it was your third branch, which was 0.167. So 0.167. And dividing those two probabilities together, it would be approximately 0.769. So this is a conditional probability again. The probability of A given B, if you have a table, you do not have to look at the rule in details. But if you have a tree diagram, then you must pay a close attention to the rule, which is the probability of A given B is equal to the probability of A and B, which is the intersection between the two events, divided by the probability of B. For E, they're asking you, find the conditional probability that the child spun blue, given that the child got a pig. So you want to figure out that it's a blue, given that you get a pig. So again, this is a conditional probability, so it would be the probability of A and B, which is the intersection between the two events, divided by the probability of B. So it would be the probability of a blue and pig divided by the probability of pig. Now, the probability of a blue and pig, it will be your fifth branch in your tree diagram that we just did in A. So the probability of a blue and pig was 0.2 divided by the probability of a pig. And the pig could be either coming from the red box or the blue box. So the probability that comes from the red box, it was 0.16 plus the probability of that's coming from a blue box, which is 0.2. So it's 0.2 divided by their sum, which should equal to, if you did your calculations correctly, it should be 0.545. So it's approximately 54.5%. Following question. On the midway at the county fair, there are many popular games to play. One of them is flip to spin or roll. First, the player flips a coin. If a head comes up, the player gets to spin the big wheel, which has 10 equal sections, 3 red, 3 blue, and 4 yellow. So let me just highlight that stuff here, because we need this information. If the coin shows a tail, the player gets to roll a cube with 3 sides, 2 yellow sides and 1 blue side. If the wheel spin lands on blue, or if the blue sides of a cube comes up, the player wins a stuffed animal. So let's put this one in our concern, and I'll highlight it here while we're doing over this question. So think about it. You have a coin, and you can flip that coin into heads or tails. If you get a head, then you can spin a wheel which has 10 equal sides. You have 3 red, 3 blue, and 4 yellow. If you get a tail, then you have 2 yellow, like you have 2 yellows and 1 blue. And additionally, if the wheel spin lands on blue, or if the blue side on the cube comes up, the player wins a stuffed animal. Let's go for the first one. Draw an area model to represent the sample space for flipping to spin or roll. So I'll start by doing my two-way table. Actually, it's a 3x2. So it's a two-way table. I need to change this one to, okay. So here we go. So here I will have heads or tails. The heads will come up half of the time. The tails will come up half of the time. And I'm not going to be specific with dividing the areas equally. So, but I know from the heads, I'll have red, blue, or yellow. And for the tails, I can get red, blue, or yellow again. And again, I'm not trying to do it like, by actually making equal areas that represents the probability. But, for the red, it's 1/3 for getting, if you get a head, then you're getting 3 reds, 3 blues, and 4 yellows. So 3 out of the 10. 3 out of the 10 for the blue, but for the yellow, it had 4 out of the 10, which simplifies to 2/5. For if you get a tail, then you have 3 red, 2 yellow, and 1 blue. So the probability of getting a red would be 3 out of the 10, 3 out of the 6 actually, which simplifies to 1/2. The probability of getting a blue is 1 out of the 6. I cannot simplify this one any further. The probability of getting a yellow, it's 2 out of the 6, which simplifies to 1/3. Now I need to figure out how can I fill up my two-way table. The probability of getting a red and a head would be 3/10 times the 1/2, which is 3 out of 20. And that simplifies to 0.15. The probability of getting a blue and a head would be 3/10 times the 1/2, which is 3 out of the 20, which simplifies again to 0.15. The probability of getting a yellow and a head would be 2/5 times 1/2, which is 1/5, and that simplifies to 0.2. Second row, you have the probability of getting a red and a tail, which is 1/2 times 1/2, which is 1/4, and that simplifies to 0.25. The probability of getting a blue and a tail would be 1/6 times 1/2, which is 1/12. And that simplifies to 0.083. The probability of getting a yellow and a tail would be 1/3 times 1/2, which is 1/6, and that simplifies to 0.16. Suppose that Tyler won a stuffed animal. Discuss with your team and then shade the appropriate parts of the modified area model to help you figure out the probability that he started off by getting a head. Be prepared to share your ideas with the class. So at this point that if he, like I tried to highlight this one into pink in the beginning of the problem, that this person will win if he gets some blue. So this is our given thing. So you want to know that this is your given, or the slash that we've been working on. So you want to figure out the probability. You started off with a head, but that you have one, which is a blue. So you want to find the probability that you're given, like you get a head, given it was a blue. So the probability of a head and a blue, it will be this box, which is here. I highlighted that now. And divided by the probability of blue, which is those two boxes together. So in order for me to write this information, the probability of a blue and a head divided by the probability of blue. The probability of a blue and a head would be the 0.15 divided by the probability of the blue, so it doesn't matter whether it was a head or a tail, so it was 0.15 plus the 0.083, the two boxes. And simplifying this one further, I should get 0.643, so it's approximately 64.3%. Following question. Raul is conducting a survey for the school news blog. He surveyed 200 senior class students and found that 78 students had an access to a car on a weekend. So you want to fill up this information. You want to build up your two-way table, but you know there's 200 senior students in your school. So I'll put here that those are the 200 senior students that Raul surveyed. Out of them, 78 had access to a car. So out of all of the 200 that had an access to a car is 78, so I'll put the 78 here. Also, 54 students had regular chores at home, so 54 had chores at home, so I'll put the 54 here because I do not know whether they have a car or do not have a car, but you know that the total people that out of the 200 that had chores were 54. And 80 students neither had an access to a car and did not do any chores. So this would be this box here. So you have all of the information that was given to you in this table at this point. Now it's your chance to figure out the remaining of this two-way table. Those two numbers, the car and no car, both of them add up to 200. So 200 minus the 78 will give you 122. So think about it as a puzzle. You're trying to find the remaining pieces. 54, which is the people that do chores or do not do chores, both of them should add up to 200. So 200 minus 54 will give you 146. Also, the people that have a car and no chores and the people that do not have a car and no chores, both of them add up to 146. So 146 minus the 80 should give you 66. Now I also know that those two boxes add up to 122. So this box should be 42. And those two boxes also add up to 78. So this box would be a 12. 12 plus 66 is 78. So we completed this table. And they're asking you here, is there an association between car privileges and regular chores for this group? So you want to figure out, it's again an association problem. So the rule that you're depending on is the probability of A, is that equal to the probability of A given B? If they were equal to each other, then you know eventually then they're independent. If they're not equal to each other, then they're associated. So equal will result into independent, and not equal will be associated. Now, if I chose my car, privilege would be my A, and chores would be my B. So I want to figure out what's the probability of car. And the probability of having a car is 78, but it's out of your grand total. So it's 78 out of the 200. Which simplifies to 0.39. The probability of a car given chores is equal to 12 out of the 54. So out of the people that have chores, which is the 54, how many of them have a car? So it's 12 out of the 54. It's a conditional probability. Remember that you're dividing by either a row total or a column total, depending on the question that you have. So it will be 12 out of the 54, and that simplifies to 0.22. Both of those probabilities are not equal, so you can say that the events are associated. So the events are associated. Last question of this lesson. There are 30 students in this class, 18 boys, and there are 12 girls. So you have 18 boys and 12 girls. If you chose a student at random to take attendance, 4 of the boys had previously taken the folder to the office and 3 girls have previously taken it. So I'm going to build up my two-way table. And with my two-way table, I'll have here boys and girls. So I'll put here boy, girl. I'll put here on the top, this is my second event, which is previously taken the folder to the office. So I will say here previous compared did not previously, so not previous, which is not previously taken the folder to the office. You know, there is a total students of 30 students. So I'll say that this is my grand total here. I know that there is 18 boys, 18 boys, and there are 12 girls. 4 of the boys have previously taken the folders to the office, and 3 of the girls have previously taken it. So I know that this would be, the 4 would be right here, because 4 of the boys have previously taken the folders to the office, and from the girls, 3 of them have previously taken it. Now it's my time to figure out the remaining of this one, of this two-way table. 4 plus a number is equal to 18, so this must be 14. 3 plus a number is equal to 12, so this must be 9. Those two, 4 plus the 3, add up to 7. 14 plus the 9 add up to 23. Now I complete my two-way table and I'm ready to do B and C. The first question, if a student is chosen at random, what's the probability that the student is a girl? So the probability is, you want to figure out the probability that the student is a girl. Or, so now this is the union of the two events. Or a student that has taken the folder previously to the office. Or, so I'll put here, taken the folder. If you recall the probability of an or, which is the union of the two events, we did this one previously in a previous chapter. So the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And we did this one, so we're not counting the people, some of the people twice. So the probability of being a girl plus the probability of taking the folder previously to the office minus the probability of being a girl and took folders to the office. So the probability of being a girl is equal to 12. There's 12 out of the 30 plus the probability of taking the folder previously to the office. So it's 7 out of 30 minus the probability of a girl and took the folder to the office, and that would be this box, which is the 3 out of the 20, out of the 30. And that results into 16 out of 30. So here you have the probability of a girl or took the folder to the office. Remember, this is the union of the two events. Last question. If a student previously took the folder, what is the probability that the student is a girl? So you want to figure out, this is a conditional probability, and you want to figure out what's the probability that you have a girl given that you took the folder to the office. So there are 7 people that took the folders to the office. Out of them, there are 3 girls. So 3 out of the 7 will be the probability of being a girl that given that they took the folders to the office. Now, there is a question, a long question that I gave you for homework. So please complete that question and upload it into Google Classroom along with the notes for this class. Thank you and have a great day. Bye.